Hello there, welcome to this video where we're going to take a look at a mathematics problem that I've selected from a sixth term examination paper. So I'll leave a link in the description to this video to the past papers for the sixth term examination papers, the set papers, so you can download whichever paper you need. It's the 1987 sixth term examination paper that we're going to be looking at in this video. So it's step 3 from 1987, and it's the first problem on that paper. Now, this is going to be a fairly long and intense video. I know, because this is the second time I've tried to record it. The first time I wasn't happy at all with how it turned out. But it's going to be quite a long video. What I would recommend is that you're prepared to pause the video from time to time, that you're prepared to take notes, rewatch certain parts. It's going to be quite a challenging video for me to make and potentially for you to watch. Okay, so you're going to have to bear with me from time to time. There's a lot to explain. So, going back to 1987, I understand that obviously that's 38 years ago, as of the time of making this video, 2025. So obviously the specifications for A-level maths and further maths will have changed in that time quite considerably. A lot of stuff has been taken out. I wouldn't say so much has been put in. It's really more the case that stuff has been taken out. But nevertheless, if you are preparing for a step exam, or MAT, or even your just normal further maths exams, going right back even to the step papers from the 1980s is well worth the effort. The problems that you will encounter on the step papers, the past papers from the 1980s, early 1990s, you will find that they're considerably more challenging than the kinds of problems that you will encounter on more current or more recent step papers. And this is good for you to develop your problem solving skills, okay? If you do balk at the fact of having to potentially learn things that are not on the current specification and things like this, really you want to be asking yourself whether doing a step exam is something that you want to be doing, because in my opinion, the more you can learn about mathematics, to a certain extent, the better prepared you're going to be for a step exam. Now, technically, you don't need to know anything beyond the bog standard specification material to do a step paper and potentially be successful. In reality, though, you do. Okay? And I'm not talking about specific techniques, I'm talking about your problem solving mindset. Okay, so yeah, obviously you're not going to be asked to use certain techniques that you wouldn't be expected to know about, but you will be expected to think about things in certain ways. Okay, and going right back to the problems on the 1980s and 1990s step papers will really get you thinking in quite in certain ways about problems. Okay, so as I've said, this is going to be a long video. This is not meant to be a model solution to this problem. This is my solution. The whole point of these videos is that I demonstrate the problem solving process. So how this is going to work is that eventually, yes, at some point in the video, I'm going to present my final solution to this problem. It's my solution. It's not a mark scheme solution. It's not something that I've just taken from a mark scheme or anything like that. It's my solution that I've come up with myself, which may or may not agree with any model solutions on any mark schemes. But for my solution to come about, there was a lot of work involved. Okay, so there was quite a bit of trial and error involved. There was a bit of a couple of false starts that I had, ideas that I tried to use that didn't quite work out the way that I wanted them to work, expected them to work out, and things like that. I'm going to be talking about all that kind of stuff. So, because that's part of the story, that's part of the problem solving process. What I'm interested in here is not really the specific problem, and it's not necessarily the specific solution to that specific problem. It's how that solution came about. Because one thing that I find from my personal experience of working with GCSE and A-level maths students is that it's all well and good knowing how to do this, how to do that, how to do the other. And what they have difficulty with is what motivates you to do certain things when trying to solve a problem. So unfortunately, the way that solutions to problems are presented in textbooks and in the classroom is that everything appears to just come out naturally, first time, perfectly, every time. That's not problem solving. That's not how it works at all. Problem solving is a dirty, messy, frustrating process. Okay, that's what I felt when I was trying to solve this problem. You might think, well, why do you do it then? Because the reward is when you find a solution to a problem, you know that you've learned something and you've had to work for it. You've had to root around for it, for the solution. You've had to tweak it here and there to make it work. You know that you've learned something. You've done something that you didn't necessarily expect to be able to do. You feel a sense of achievement. That's the whole point of it. Yes, it's frustrating. I want to present in a way the problem solving process in a much more accurate light. Okay, I don't want to present it. I don't want you to get the impression that problem solving is just this nice, easy thing, because it's not. Okay, if you think that, you're in for a shock. Okay, so bear with it in this video. It's going to be long. To make things easier for yourself, it would help if you're thinking about factorials. We're going to be using factorials a lot. We're going to be using the fundamental theorem of arithmetic. Now, I'm going to briefly touch on these as and when they come up, but I'm not going to be going into detail with them. What I would encourage you to do is to do your own independent research. If you're not too familiar with factorials, okay, go away and familiarize yourself with factorials. If you're not too familiar with fundamental theorem of arithmetic, you know what to do. Okay, so let's get on with the problem. I'm a little bit nervous about this because this is going to be a difficult video for me to make. Like I said, this is my second attempt at making it. So question 1 from the 1987 Step 3 examination paper. Find the set of positive integers n for which n does not divide n minus 1 factorial. Okay, so on the one hand we've got n, on the other hand we've got n minus 1 factorial. We need to find the set of positive integers n such that n does not divide n minus 1 factorial. Importantly, it says justify your answer. Okay, well, we're mathematicians. That's a natural thing to do. We don't really need to be told to justify our answer. We are given a little bit of a hint. Note that the small values of n may require special consideration. It doesn't say which small values of n. It doesn't. What's meant by small in mathematics could mean all sorts of things. It could mean the 1, 2, and 3, or it could mean anything up to 10 billion, for example, or even more. So we're going to have to exactly what that hint is referring to. It's not necessarily clear to us right now. We're not going to be concerned with it. What we're interested in first and foremost is actually getting a rough idea about how we're going to attack this problem. The main part of this problem. The fine details, they can always be ironed out further down the line. Don't worry too much about fine details. It's important for you to just generate ideas and try to start developing those ideas. Okay, if you get an idea that develops far enough, then you can start to think about the finer details. And it might put a bit of a spanner in the works every now and again. When you start considering the fine details, it might throw things off a little bit, but that's a better way to go about things rather than trying to incorporate all the fine details from the start. Okay, so first of all, make sure that you know what is meant by a factorial. So n factorial, for example, is equal to n times n minus 1 times n minus 2, all the way down to times 2 times 1. In other words, n factorial is the product of all of the positive integers from 1 to n. Okay, that's n factorial. Importantly, that means that in n factorial, every positive integer less than or equal to n is a factor of n factorial. Okay, that it seems like a trivial observation to me. That's going to be terribly important for us to bear in mind. Okay, so in other words, if n is equal to 67, that means that 25 is a factor of n factorial. 53 is a factor of n factorial. 10 is a factor of 67 factorial. Sorry. Okay, this is going to be really important. Okay, so the first thing that popped into mind with this when I wanted to try to find a solution to it was fundamental theorem of arithmetic. Okay, so the fundamental theorem of arithmetic, and again, you really make sure that you understand thoroughly enough what the statement of this theorem is. It says that for any positive integer, any integer greater than or equal to 2 has a unique prime factorization or prime factor decomposition, however you want to term it. Okay, so for example, we can take the number 70. Okay, 70 is equal to, let me think now, 2 times 3 times 7. No, it's not. 2 times 5 times 7. 2 times 5 times 7. So, okay, admittedly, we could write, for example, 2 times 7 times 5, or 5 times 2 times 7. But the fundamental theorem of arithmetic considers all these the same. So we've got 2 times 5 times 7. Any permutation of these is also going to be, it's going to be considered the same factorization. The point is, there's no other way that I can split 70 down into a product of prime numbers other than with a 2, a 5, and a 7. Okay, and this applies to any positive integer greater than or equal to 2. Very, very, very important. Okay, let's take the number. You've come across prime factorizations probably when you did GCSE Maths, when you did factor trees and all that kind of stuff. So let's take the number 90, for example. You might do that. I mean, there's different ways that you can do it. You can split it down into 9 and 10, and then split 9 down into 3 and 3. They're prime numbers, so stop, and then 10, 2 and 5. Okay, so we get 90 is equal to 2 times 3 squared times 5. Okay, but again, there's no other way that we can express 90 as a product of prime factors other than 2 times 3 times 3 times 5. Okay, notice that it's normal for you to express, if you've got multiple instances, multiple factors of a particular prime, expressing them as a power of that prime. So rather than writing 2 times 3 times 3 times 5, 2 times 3 squared times 5. And wherever possible, I guess it makes sense to write the primes in kind of ascending numerical order, though that's not essential because of this, the fact that any reordering we consider equivalent to this. Okay, so why did I think about this? Well, it just seemed like a natural thing to think about, to be honest with you. But for example, let's say we've got n equals p1 to the power of alpha 1, p2 to the power of alpha 2, up to pk to the power of alpha k, where we've got p1, p2, up to pk. These are distinct primes. And the alpha 1, alpha 2, up to alpha k, these are positive integers. So integers greater than or equal to 1. Okay, so remember prime numbers 2, 3, 5, 7, whatever. Okay, so this just seemed like a natural thing for me to consider. At first, I didn't know exactly how this was going to be useful, But this is, again, part of the problem solving process. You've got to have ideas, you've got to try out ideas, and you've just got to see where they go. Okay, if I tried this and it led nowhere, that's it, so be it. Okay, but that's not the case. This did lead somewhere. Now, first of all, the first attempt at a solution that I made was wrong. Okay, I'm going to go through it because it did actually motivate me, and I want to show how it motivated my final solution to this problem, because this is the thing that people often get stuck with, is how did, rather than me just presenting my solution and saying, oh yeah, do this, do that, do the other, people then are confused about how did I know to do that? Why did I choose to do this? How did I know that was going to work? In some cases, it's just gut feeling. Sometimes you just have a feeling that something's going to work. Sometimes you don't know that something's going to work, but you just think it might do. In other cases, there might be something that kind of triggered an idea. It didn't necessarily trigger a complete, coherent idea, but it started giving you a push in the right direction. Okay, so the first attempt that I had at a solution to this problem, which I initially thought was right and turned out to be wrong, kind of motivated my latter attempt that I consider to be correct. I hope. Okay. And I am going to have to refer to my notes throughout this because there's a lot to remember. So, the question that I asked, instead of as it is on I've got it up on my computer screen here, so if it looks like I'm looking beneath the camera, that's because I am. The problem asks us to identify those positive integers that do not divide n-1 factorial. But I instead thought it might be easier for me to think about could I identify which positive integers n do divide n-1 factorial? Okay, and what would that look like? Now, this might seem like the complete opposite to what it is that I'm trying to show. What's the point in that? Well, if you think about it, if I can identify which integers do divide n-1 factorial, then what are left do not. And it might be easier for me to identify those integers n which do divide n-1 factorial, and indirectly, therefore, identify those that do not. Okay? Sometimes this is just what you've got to do. Did I know that this was going to work? No, it's just that this is what seemed easier to me to do. So just be prepared to use your ideas, okay? Right, so something else that what I thought about then is, if n is going to divide n-1 factorial, what must be in n-1 factorial? So if we think about n-1 factorial, there must be, for n to divide this, there must be alpha 1 factors of p1. There must be alpha 2 factors of p2. And so on and so on and so on. There must be alpha k factors of pk. So if n divides n-1 factorial, then there must be alpha 1 factors of p1, alpha 2 factors of p2, alpha k factors of pk. So that led me to consider this array of numbers now. So the array of numbers p1, 2p1, 3p1, up to alpha 1 p1. Okay, p2, 2p2, 3p2, up to alpha 2 p2. pk, 2pk, 3pk, up to alpha k pk. Okay, so what I did initially and inadvertently, and those of you who are paying attention will know that what I'm about to say is wrong, and I acknowledge that it's incorrect. my initial assumption was that all of these numbers, P1, 2P1, 3P1, and so on, will all be distinct. Okay, in other words, no numbers will be repeated. This is a very naive assumption that I've made, and it was made in the heat of the moment. And things like this will happen again when you're trying to solve a problem. Your mind will be on a million things sometimes, and yeah, you'll make an assumption, and then when you come back to it and further down the line and you analyze it in a bit more detail, you realize it's wrong. This assumption is wrong, but it does lead to something useful for me. Okay, so I considered this array of numbers, and I made the assumption, again, incorrect assumption, that all of the numbers in this array are going to be distinct. Okay, so if that's the case, and let's run with that for now. So let's get rid of some of this stuff here. So just clear a bit of space. If I can find let's suppose I choose the maximum value that I find amongst all of these numbers. Well, it's going to be, the maximum is going to be one of these alpha I, pi. So it's either going to be alpha 1, p1, or alpha 2, p2, alpha 3, p3, or alpha k, pk, for example. So let's say that we've got the maximum over the alpha I, pi is equal to alpha p. Okay? Still on the assumption that all of these numbers are distinct. So therefore, if I can find that n minus 1 is greater than or equal to alpha p, then n minus 1 factorial is going to be greater than or equal to alpha p factorial. Now, because alpha p is the greatest number in this array, then what that means is that in this factorial, alpha p, all of these numbers will appear somewhere as factors. Remember what I said? N factorial, all of the integers less than or equal to n will appear as a factor somewhere in that factorial. So all of these are integers. Alpha p is the greatest amongst them. So therefore, all of these numbers will appear as a factor in alpha p factorial. Again, still on this incorrect assumption that all of these are going to be distinct. We're just going with that idea. So then I thought, what would I need to show for n minus 1 to be greater than or equal to alpha p? So I'd not realized at this stage this problem. Okay, what would I need to show? And by the way, all of these numbers appear as a factor in alpha p factorial. That means that there's going to be alpha 1 factors of p1. There's going to be alpha 2 factors of p2. There's going to be alpha k factors of pk, which means that n will divide n minus 1 factorial. That's the whole idea behind it all. Okay, so what I would potentially need to show, one thing that I could show is that if I could show that p to the power of alpha is greater than alpha times p for a prime number to the power of alpha, that this is greater than alpha times p. Or let's cast it in terms of the i's here. So let's say pi to the power of alpha I is greater than alpha I times pi, because in that case, n will be greater than pi, greater than or equal to pi to the power of alpha I. Maybe I should have stuck with p and alpha actually. It's going to be greater than or equal to p to the power of alpha. Remember, p alpha is the greatest amongst these alpha I, pi, greater than alpha p. So that means that n minus 1 is going to be greater than or equal to alpha times p. Right, so why is that, by the way? Well, if x and y are positive integers and x is less than y, then x plus 1 is less than or equal to y, or conversely, y minus 1 is greater than or equal to x. So this strict inequality can be turned into a weak inequality in one of two ways. So I'm using this, effectively this way, subtracting 1 from n. So we've got n is greater than alpha times p, so n minus 1 is going to be greater than or equal to alpha times p. Generally speaking, n is going to be much larger than alpha times p, but this is sufficient for me to carry my argument through. Okay? So my job is then to prove that p to the power of alpha is greater than alpha times p for some prime number and a power. Now, it turns out that there are certain restrictions that we need to include here for this to work. And I do need strict inequality. I can't have weak inequality, and that's why I've got to exclude certain cases. Okay? Because if I can do this, then what I can say is that n minus 1 factorial is greater than or equal to alpha p factorial. Therefore, if this is kind of the maximum of the alpha IPI, then we get the sufficient number of factors of P1, sufficient number of factors of P2, and so on and so forth, and we get n divides alpha times P factor, or n divides n minus 1 factorial. Okay, so what we want to prove then is this inequality here, that p to the power of alpha is greater than alpha times p. We're going to do this by induction, okay? So if you're not familiar with proof by induction, have a little read around proof by induction. It's not terribly involved what I'm going to be doing here, but let's have a look at how it's going to work out. So we've got a problem when it comes to, for example, 2 to the power of 1, because 2 to the power of 1 is equal to 1 times 2. Okay, so in that case, 2 to the power of 1, p to the power of alpha is not greater than alpha times p. It's only greater than or equal to. Okay, it's equal to, but we can still say greater than or equal to. Similarly, 2 squared is greater than or equal to 2 times 2. 3 to the power of 1 is greater than or equal to 1 times 3. In fact, any prime to the power of 1 is only greater than 1 times p. So this places some restrictions because it is this strict inequality here that I'm relying on. So what we've got to kind of exclude these cases. So what I'm going to be looking at then is two possible cases. We've got p to the power of alpha, where p is a prime greater than or equal to 3, and alpha is an integer greater than or equal to 2. So that excludes all of these cases, and I guess that case as well. Actually, yeah, excludes that case. And we're also going to need to consider 2 to the power of alpha, where alpha is greater than or equal to 3, and that excludes that case. Okay, so let's look at p. The base case here is p squared. P squared is equal to p times p. P is greater than or equal to 3, so that's going to be greater than or equal to 3p, which is greater than 2p. Okay, so that's the base case proved. So now assume for some fixed k that p to the power of k is greater than k times p. So that means that p to the power of k plus 1 is greater than p times k times p. Okay. P times k times p. Now p times k is going to be greater than 2k. I think I'm doing this. Hope I'm doing this right. So that's that's greater than 2k times p, which 2k times p is k times p plus k times p. K has to be greater than or equal to 2. So this is going to be greater than k times p plus p. K is greater than or equal to 2, which is of course equal to k plus 1 times p. In other words, p to the power of k plus 1 is going to be greater than k plus 1 to the k plus 1 times p. By mathematical induction, therefore, p to the power of alpha is going to be greater than p to the power of alpha is greater than alpha times p for all alpha greater than or equal to 2. For all integers alpha greater than or equal to 2. We can do a similar argument for this. I'm not going to go through it in all its detail, but we get a similar result with this. Okay, so what we end up with are the following inequalities, which are going to be critical for my argument henceforth. So we've got p to the power of alpha is greater than alpha p. For p, a prime greater than or equal to 3 and alpha greater than or equal to 2, an integer, and 2 to the power of alpha is greater than alpha times 2 for alpha greater than or equal to 3. The cases that I've excluded from this are going to be, we're going to have to consider those individually, okay? And the hint that we're given where we need to give special consideration to small values of n kind of ties in with this, okay? At least as far as I can understand the situation. So, if we're still under this erroneous assumption, by the way, that all of those numbers, p1, 2p1, up to alpha 1, p1, all of the numbers in that array are all distinct numbers. We're still working on that assumption right at this moment in time. Okay, so what this means is that if n is equal to this, then n is going to be greater than or equal to p to the power of alpha. So remember, p to the power of alpha p is the maximum. Sorry, I'm writing this the wrong way around here. Alpha p is equal to the maximum of the alpha I pi. Okay, so n, because it's the product of all of these primes, we're kind of selecting one of these out that satisfies this. And therefore n is necessarily going to be greater than or equal to p to the power of alpha. And which is under the suitable conditions, which I'm not going to make a big deal about all of the fine details, because again, this argument is really only the motivation. It turns out it only provides the motivation going forward. That's going to be greater than alpha times p. So therefore n minus 1 is greater than or equal to alpha p. Therefore n minus 1 factorial is greater than or equal to alpha p factorial. And therefore n divides alpha p, n minus 1 factorial. And based on this, what I did then was I considered various cases. Okay, there was some. This considers one possible case, for example, where p is greater than or equal to 3, alpha is greater than or equal to 2. Then it's simply we need to do some case analysis. Okay, look at different categories. So there are exceptions to these that we need to consider separately and individually, or even subcategories that we can consider the whole subcategory, or we can consider individual elements of the whole category. Okay, so this is a very common thing to do when trying to prove things in mathematics, that you want to prove something for a whole category of objects, but it might be that that whole category, it's difficult for you to attack the problem based on the whole category all at once. So what you might need to do is to kind of split the category down into subcategories. So non-overlapping subcategories, but subcategories that exhaust all of the possibilities. Okay, so there's no elements that have been left out. So if this is your whole category, then your subcategories, diagrammatically might look like this. So they don't overlap, but they also include all possibilities. Okay, so you've got category A, B, C, D. And sometimes there can be a few categories, sometimes there might be many. So what I did here was I kind of split all of the possible values of n down into certain categories based on the form of their prime factor of its prime factorization. And I dealt with them separately, and I got to a solution. Some of them I was able to show some values of n do divide n minus 1 factorial, and in other cases n does not divide n minus 1 factorial. That was my solution, and it was based on that erroneous idea that all of the numbers in that array were going to be distinct. Then I realized what the problem was. The numbers in that array are not all going to be distinct. And I'll give you a simple example to show how that can happen. So if we take, for example, 3 to the power of 5 times 5 to the power of 7, we get 3, 2 times 3, 3 times 3, 4 times 3, 5 times 3, right? So in this case, we've got P1 is equal to 3, P2 is equal to 5, alpha 1 is equal to 5, alpha 2 is equal to, not 5, 7, sorry, 3. Alpha 2 equals 3. Then we get on the next row 5, 2 times 5, 3 times 5. Well, 3 times 5 is equal to 5 times 3. They're both equal to 15. Okay, so in other words, in that big array, not all of the numbers are going to be distinct. So what that means is, and I only realized this a few minutes after I'd finished writing up my first attempt at this solution. What it means is that in this factorial, alpha p factorial, there might not be enough factors of P1. There might not be enough factors of P2. There might not be enough factors of PK. There might be, and it might be possible to come up with a sufficiently convincing argument, and true, obviously, that shows that is the case. But if such an argument exists, it's probably going to be very fiddly, and it's probably going to be quite involved, and it's probably going to be more effort than it's worth. It's kind of unnecessary. So it was back to the drawing board. I was thinking, okay, how, even with repetitions in here, how can I guarantee that in n minus 1 factorial, I'm going to have alpha 1 factors of P1, alpha 2 factors of P2. And this is where I hit on the idea that this is still exactly what I need. Okay, but rather than trying to find the maximum over the alpha IPI, I just use basically all of them. Okay, so let's have a look how that's going to work. And now this is where we start getting into the different, potentially considering the different cases. So there's 7 or 8 different cases that we're going to need to consider. So you're going to have to really bear with it, okay? There might be a more efficient solution. I am not going to suggest that the solution that I'm about to give to this problem is the best solution. I'm not suggesting that at all. It's just my solution. I'm happy with the solution for the time being. I've got no intention of trying to find a better solution at this moment in time. It is what it is. Okay, so let's get rid of this. So I'll illustrate what my thinking was on a kind of smaller scale. So let's say we've got, for example, n equals just P1, alpha 1, P2, alpha 2. Okay? Then, in fact, no, I don't even need to set n equal to that. Let's just consider this number. Okay? And let's just assume that we want to find sorry, not that number. Alpha 1 times P1, alpha 2 times P2. And I want to consider the factorial of this. Now understand that the numbers that are involved here are potentially enormous. There is no way of comprehending really the enormity of these numbers. They are absolutely astronomical would be an understatement. So we've really got to rely on the algebra to tell us what's going on. So alpha 1 P1, alpha 2 P2, all factorial. So the first number is going to be, the first factor is going to be alpha 1 P1, alpha 2 P2. And this is going to reduce by 1 each time until eventually I get to alpha 1 minus 1 times P1, alpha 2 P2. Carries on, and I get to a stage where I get alpha 2 minus 2 P1, alpha 2 P2. Carry on. Eventually I get to 2 P1, alpha 2 P2. Carry on. I get P1, alpha 2 P2. Carry on. What do I get to? I get to alpha 2 P2. Carry on. I get alpha 2 minus 1 times P2. Carry on. I get to 2 P2. I get P2. I get times 2 times 1. Right, so repeatedly subtracting 1, you eventually get to this. Repeatedly subtracting 1, you eventually get to this. Repeatedly subtracting 1, you eventually get to this. So this will happen after however many steps. You figure it out, I don't know. A lot of steps. But the point is that I can guarantee, based on what I see here, that I'm going to have, I've got a factor of P1 here. I've got a factor of P1 here. I've got a factor of P1 here. I'm going to have how many? 1, 2, 3, alpha 1 minus 1, alpha 1 factors of P1. Then I start with the P2. I've got a factor of P2 here, factor of P2, factor of P2, factor of P2. How many am I going to have? Alpha 2 factors of P2. Right, this is great. This is great because I've got a way now of guaranteeing enough factors, right? So let's go back to this, and we're going to be considering some very specific cases. Okay, some very specific cases. And all I can say is that these specific cases came about gradually. So there's about seven or eight cases that we're going to be considering. It is not the case that I knew that I was going to need to split all integers down into these 7 or 8 cases from the outset. It's just something that gradually emerged in my mind. Because sometimes you try something and it doesn't quite work, and you see how you can tweak it and to make it work, but then that kind of causes a bifurcation, right? Then that category, what you were originally considering as a single category, now splits into 2 separate categories. And it might be that one of those categories, subcategories, splits into 2 more categories, okay? Or something like that. So I'm not going to go through the whole story about how these categorizations came into being in my mind, and I'm not suggesting that they are optimal or anything like that. So let's have a look. So if, this is case number 1, n equals P1 to the power of alpha 1, P2 to the power of alpha 2, up to Pk to the power of alpha k, times Pk plus 1 to Pr. Okay, so all of the P1, P2, up to Pk, Pk plus 1, Pr, these are all distinct primes. Okay, there's no restriction on those at this moment in time. However, we've got alpha 1, alpha 2, up to alpha k. These are positive integers greater than or equal to 2. Okay, so this is the first case that I'm going to consider. So let's have a look. Again, I am going to have to refer to my notes because it's not the most straightforward thing in the world. deal with here. Pi is greater. Aha, sorry, right. These primes here, P1 to PK, have to be greater than or equal to 3. But the PK plus 1 to PR, they can just be greater than or equal to 2. Okay, so there is a further restriction that we're applying here. These primes here have to be greater than or equal to 3. These primes have to be greater than or equal to 2. In other words, these can be any primes as long as they're distinct with each other and distinct from each of the P1 to PK. Right, so what's the point here? Well, in that case then, since we've got P1 alpha 1 is greater than alpha 1 times P1, P2 to the power of alpha 2 is greater than alpha 2 times P2, Pk to the power of alpha k is greater than alpha k times Pk. What that means is that all of this together, P1 alpha 1, P2 alpha 2 to Pk alpha k is going to be, I'm going to write it over here because I'm going to be writing something else in a second. This is going to be greater than alpha 1 P1, alpha 2 P2, alpha 3 P3, up to alpha k Pk. I've gone a bit overboard there. Okay, so that means that multiplying each side of this by Pk plus 1 up to Pr, we still preserve the inequality. So this is equal to n. So n is equal to this, which is greater than this. And therefore, n minus 1 is going to be greater than or equal to this horrible thing here. Alpha 1 P1, alpha 2 P2, up to alpha k Pk. Don't you just love maths? Having to write out these horrible expressions. So that means that n minus 1 factorial is going to be greater than or equal to this factorial. So what do we have in this factorial? We're going to have alpha 1 factors of P1. We're going to have alpha 2 factors of P2. We're going to have alpha k factors of Pk. We're going to have a factor of Pk plus 1. We're going to have a factor of all of these primes up to Pr. Therefore, n divides n minus 1 factorial. Okay? But they're the conditions that we've had to apply to this. It's a very specific category. Again, I'm not going to go into detail at this stage how this came about, but it really is by considering this, I need to guarantee the strict inequality here. If I've got a weak inequality here, that's special considerations. Okay, so, right, let's put a tick next to that one. On to case number 2. And by the way, this is just the order that the cases came to me. There's no specific logical order that I'm doing these in. Some of the later cases are going to seem straightforward compared to these, and you might think, well, why didn't I do those first and things like this? Because I'm presenting my solution basically as it came to me. Okay. Again, I don't really want to present the problem-solving process as something that's nice and straightforward and everything comes out nice and perfect. There's often several iterations involved in solving a problem. Okay, so what this means is that as long as if I've got n is equal to a product of primes, it can be products of any primes, but if there's a factor, if there's a prime that has a power greater than a prime in that factorization that's greater than or equal to 3 and which has a power greater than or equal to 2, then n must divide n minus 1 factorial. Okay, so something like if n equals 7 squared times 5 to the power of 8 times 3 to the power of times 3 times 2, for example, this will divide n minus 1 factorial. Okay, based on what I've shown here. Okay, God knows what n minus 1 factorial of this is going to be. It's going to be an absolutely enormous number, but it's beside the point anyway. So what's the second case that I'm going to consider? I don't know. I can't remember off the top of my head. Let's have a look. The second case. Right, okay, so if n is equal to a product of distinct primes, so n is equal to p1, p2 up to pk, where k is greater than or equal to 2. So specifically, these are distinct primes, and there's at least 2 distinct primes involved. Okay, so the pi are distinct primes. No restriction on their value. So in that case, this is a little bit easier to deal with because if I choose p equals the maximum over the pi's, then because of this, the fact that k is greater than or equal to 2, then n must be greater than p. Okay. So in that case, then n minus 1 is greater than or equal to p, and therefore n minus 1 factorial is greater than or equal to p factorial. Okay, so remember what I said right at the start. For n factorial, all integers less than or equal to n, right down to n minus 1, n minus 1, n minus 2, all the way down to times 2 times 1. All positive integers less than or equal to n is a factor. Each positive integer less than or equal to n is a factor of n factorial. So if I've chosen the maximum amongst these primes here, then all of the other primes are going to be less than that prime. Okay, so therefore each of those primes will be a factor in p factorial. The upshot, n divides n minus 1 factorial in that case. That's case number 2. Case number 3. What's case number 3? Case number 3 is when I've just got a pure prime. Okay, so n equals p, where p is a prime. Remember what it means for a number to be a prime number, very important. A prime number is effectively its own prime factorization. Okay, a prime number is divisible by 1, it's divisible by itself and nothing else. So if I've got prime number 17, I can't decompose this as a product of two numbers other than 1 and 17. Okay, but its prime factorization is just itself. Very important because that's what we're going to be using next. So if n equals p, then n minus 1 is equal to p minus 1. So therefore, n minus 1 factorial equals p minus 1 factorial. Good stuff. So what does that mean? Think about which numbers appear in p minus 1 factorial. P minus 1, p minus 2, p minus 3, times 2 times 1. P does not occur as a factor in p minus 1 factorial. Okay, what does that mean? If n is a prime number, n does not divide n minus 1 factorial. And remember, it's actually the numbers n which do not divide n minus 1 factorial that we're really interested in. So we've kind of identified one there. There's no restriction on the prime here. Initially, I did ensure that p was greater than or equal to 3. A prime number greater than or equal to 3, and then I considered 2 separately, but it's not necessary. It's not necessary to do that. So p can be any prime. Okay, so then case number 4. Again, these are just as they came to me, really. So case number 4. So now we need to start looking at powers of 2. In particular, when alpha is equal to 2 up here. So 2 to the power of 2. Remember, 2 to the power of 2 is equal to 4. So if n is equal to 2 to the power of 2, which is 4, then n minus 1 is equal to 3. So n minus 1 factorial is 3 factorial, which is 6. 4 does not divide 6. So therefore, n equals 4 does not divide n minus 1 factorial. And when, with the hint that we were given that small values of n may require special consideration, I think this is what it's getting at. There was no way for us to know that right at the start. There was no way for us to know. But I think that's what it's getting at. We're nearly there. We've only got a few more cases to consider. You'll be glad to hear. Okay, so case number 5. So we've got, I'm going to refer to my notes here because this is a fiddly one. So we've got 2 squared times p1 up to pk, where p I'm going to call the maximum of the pi, and that this is going to be greater than or equal to 5. Okay, so in that case, if this is n, then n must be greater than p. Okay, but p is greater than 4. That's going to be important, which is equal to 2 squared. Okay. Initially, we're going to be interested in this bit. That bit is going to come into play further down the line. So if n is greater than p, that means that n minus 1 is greater than or equal to p minus 1. Is greater than or equal to p. Therefore, n minus 1 factorial is greater than or equal to p factorial. So, again, p is the maximum of the pi. The fact that it's greater than or equal to 5 allows me to say this. But the fact that we've chosen p to be the maximum amongst the pi ensures that all of these primes will be a factor in p factorial, which is n minus 1 factorial. Okay, that applies to all of these primes here, p1 to pk. But what about the 2 squared? Okay, that's where this comes in, because p factorial is greater than 5 factorial. So this is greater than 5 factorial. But 5 factorial, remember, is 5 times 4 times 3 times 2 times 1. So in p factorial, we've got all of these factors as well. In particular, we've got 4. Or I can think about it, I've got a factor of 2 here, and I've got another factor of 2 here. So I've got the 2 factors of 2 that I need to ensure that n divides n minus 1 factorial. So in that case, we get, again, n divides n minus 1 factorial. Whew. Very, very close now. Very exciting. 6. So now we look at if n equals 2 squared, p1. Sorry, actually I don't need to, the max of pi. Aha, okay, no. Very specific case, 2 squared times 3, which is 12, which is kind of the case that's been excluded here, where the maximum amongst the pi is equal to 3. Well, that's the only possibility then, 2 squared times 3, because there can't be any other prime numbers because they would necessarily be greater than 3. So that means that n minus 1 is equal to 11. So n minus 1 factorial is 11 factorial, which is equal to 11 times 10 times 9 times 8 times 7 times 6 times times 2 times 1. It's very easy to see that we've got a factor of 3 in there, and we've got a factor of 2 there, and another factor of 2. Well, we've got 4 times 3 times 2 times 1. So we've got everything that we need. N divides n minus 1 factorial. Easy peasy. Okay. And then we've got, oh, is that the pi is greater than or equal to 3 prime? Okay, we've got one more case to consider. Again, I'm going to refer to my notes because I'm getting a bit lost with everything. So case number 7, we've got 2 to the power of alpha times p1 to pk, where alpha is greater than or equal to 3 and pi are greater than or equal to 3, all distinct primes. Okay, so in that case, again, we set p equal to the maximum of pi. And what do we have? So if n will be greater than, so this is equal to n will be greater than 2 times alpha times p. Why is that? Alpha is greater than or equal to 3, so 2 to the power of alpha is greater than alpha times 2 times p. Okay, and where am I? So that means that n minus 1 is going to be greater than or equal to 2 alpha p, and therefore n minus 1 factorial is greater than or equal to 2 alpha p factorial. So what does this guarantee? It guarantees that all of these primes, which are all less than or equal to p, are going to be factors in this factorial, but also because of the 2 alpha, I'm guaranteeing alpha factors of 2. Okay, so the upshot is, in this case, n divides n minus 1 factorial. And I hope that accounts for all possible combinations, all possibilities. If I've missed any, I do apologize. Please let me know. It did take me a while to figure this out. My brain was kind of thrashed by the end of this, to be honest with you. If you see anything that I've missed, please do let me know, because there is a good chance that I've missed something. Nevertheless, I think the direction of the solution is generally correct. Even if the details need some brushing up here and there, the general direction of the solution I believe to be correct. If there is anything that you don't understand that you want clarification on, please do ask. Please leave a comment in the comments section or get in touch with me. I'll be happy to help, because there's a lot to take in. I appreciate that this has been a long video, been a very difficult video to make, and it's going to be a very difficult video for you to watch. But I'm open to any questions, also any suggestions. If you do have any ideas about other problems that you would like me to kind of go through, please let me know. I'd love to experiment with some different ideas and things like that. If you did find this video useful, please show your support by subscribing to this channel. It's a very small channel at this moment in time. I am looking to upload videos, and I'm really looking to reach a wider audience. Okay, so I'm really interested in helping people who are doing step exams, preparing for step exams, preparing for mathematics admissions tests and things like this. So if you know anybody that's preparing for these exams or doing their further maths or A-level maths or anything like that, and you think these videos are going to be useful to them, please let them know about them. Please give this video a like. Again, I show your support for this video, because I don't get paid a penny for making these videos. I do them because I want to do them, and I want to help people. Okay, and I want to continue making them. So please show your support for this channel by hitting the subscribe button and hitting the like button. That brings us to the end of the solution to this particular problem, and it brings us to the end of this video. Thank you very much for watching.